Let's take that second kick at the can. What we really care about is the change in the electric potential energy as something goes from A to B. And we find that by taking the voltage from A to B and scaling it by the test charge that we're actually moving from A to B. In that sense, this voltage is a rate. When I say there's 120 volts from A to B, what I say is that's how much I would store, how much electric potential energy I would store if I took 1 Coulomb from A to B. Well, if I take 2 coulombs, I just store twice as much energy. 5 coulombs, 5 times as much energy. Okay? Now, if I remember from 205, external Verk is what changes total energy. And in these problems, when we say total energy, we mean kinetic energy and electric potential energy. We are typically dealing with things like protons and electrons that have such a small mass that we don't really care about the change in gravitational energy. It's negligible. And so if I grab that object and move it in such a way that it starts at rest and ends at rest, then there's no change in kinetic energy. And that gives us a conceptually simple way of measuring how much energy we stored in the system. Well, how much Verk did I do to cock the spring? Okay? Well, let me see if I can make that visual. There's a younger Greg Francis. If we put a bowling ball over his head, he is not, I repeat, he is not afraid. Okay? That bowling ball doesn't have the capacity to do any damage to Greg's head. And that's because it has a low gravitational potential energy. Energy is the capacity to do damage. I'm not afraid. Okay? Likewise, if I put a positive charge right here next to this negative plate, that's where it wants to be. That's its happy place. It doesn't want to be near that positive plate. It wants to be here at the bottom of the cliff. Okay? In that case, I would say it is at a low electric potential energy. Now, in order to find out how much energy that I store, I just calculate how much Verk, an external agent, the hand, has to do to take the bowling ball somewhere else, or to take the charge somewhere else. And if I lift that bowling ball, the hand is pushing in the same direction that the bowling ball is going. The hand is doing positive Verk. If we do it in such a way that we don't change the kinetic energy, that Verk, that positive Verk, is giving me a positive change in electric potential energy. I'm sorry, in this case it would be gravitational energy, right? Okay, now, what that positive change means is I move to a region of higher gravitational potential energy. When the change in your bank account is positive, you do the happy dance. That's a positive change. It got bigger. It got fuller. Okay? The bank account. Now, in the same way, by pushing this positive charge against the field, just like I was pushing this bowling ball against the gravitational field, I'm pushing this positive charge against the electric field. I'm doing positive Verk. It doesn't want to go there. I've got to push in the same direction it's going. And by doing that positive Verk, I'm storing energy. In this case, I'm cocking an electric spring. In this case, I'm cocking a gravitational spring. But either way, I'm cocking a spring. I'm storing energy. Okay? The change in electric potential energy would be positive. Now, what happens when I let them go? When I just let them go, suddenly I find I've got kinetic energy. Okay? The bowling ball has the capacity to do damage to Greg's head. The positive charge now has capacity to do damage to this plate. They have kinetic energy. Now if I go back to this original equation here, clearly it's not the change in kinetic energy that's zero now. What's zero, in this case, is the varich. The hand just let him go. Did not do any varich. Just let it go. And now we see that whatever change I have in kinetic energy has to be accompanied by an equal but opposite change in potential energy. Okay, I can rewrite this as the change in kinetic energy is equal to the change, in this case, electric potential energy, but I've got to have a minus sign there. If this is a plus 6, that has to be a minus 6, so that when I add them together I get 0. And if this is minus 6, and I multiply a minus 6 by a minus, I get a plus 6. That's what that's saying. Now, folks, where does the kinetic energy come from? When you go to sleep at night, right before you go to sleep, I don't care what you have been thinking about, from now on I want you to think about this picture here. Throughout the spring break, whatever beach you're on, this is what goes through your mind before you go to bed. Okay? What this tells me is that in order for the kinetic energy bucket to fill, the potential energy bucket has to drain. It's a zero-sum game. In order for me to get an extra 6 joules here, I got to lose 6 joules there. Now folks, when we talk about kinetic energy is 1/2 mv squared. I know what it is initially, I know what it is at the end of the motion. I just take final minus initial. But when I'm talking about the change in electric potential energy, I don't have a 0 that's set for electric potential energy. All I ever care about is how big the change is. Okay? Just like we never care where the 0 of height is, we could call it sea level, we could call it Main Street Bozeman. It doesn't matter. Likewise, the change in voltage, whether we go from 500 volts to 600 volts, or whether we go from 800 volts to 900 volts. Either way, I get exactly the same physics. So when we're talking about the change in electric potential energy, we leave it in this form. Okay? Now, the other thing that I would like you to focus on during break, when you're not on a beach, is the fact that I have the same relationship with the electric field as I have with electric voltage. They are both rates. I have this equation relating the force that I care about to the electric field as just a gimmick. Okay? I have this relationship between the electric potential energy that I care about and this voltage thing that's just a gimmick. Okay? If I set the test charge equal to 1, then I see what this gimmick is. The electric field is the electric force if the charge we're pushing on is 1 Coulomb. Okay? It's like going into a gas station where they have a big sign that says, price of gas, $2 per gallon. Any grade, $2 per gallon. And you go in and you say, hey, how much would it cost to get a gallon? Should you feel stupid? Yes, there's a sign. $2 per gallon. And that's what this is saying, is when you're getting 1 unit of charge moved, the electric field is the electric force. That's how I understand what the electric field is. Okay? If you want 2 gallons, it's $4. 3 gallons, it's $6. Do you see a pattern? Okay. The same thing is true with voltage. When I say that the voltage is 120 volts, what that means is that whenever I move 1 Coulomb of charge from A to B, I'm storing 120 joules. A volt is a joule per coulomb. I'm storing 120 joules. If I move 2 coulombs, twice that much. Okay? It's a rate. It's a rate. These are the things that we really care about. This is how we get them. Check that your neighbor's on the bus. If not, just slap them till they are.